Hello and welcome back, Chemistry 112 students. This is the first in a series of distance learning lectures that we'll use to finish up the course material for Chemistry 112 during the spring semester of 2020. My idea is to produce between 4 and 6 of these short videos per week for the rest of the semester, keeping the videos limited to between 10 and 20 minutes in length. Today, we'll finish up chapter 15. Recall, chapter 15 was all about applications of equilibria, and primarily the very back end of this chapter was about solubility equilibria. So we want to finish up with looking at both qualitatively and quantitatively some factors that may affect the solubility of a substance. So for example, we have a substance such as silver cyanide. Silver cyanide is a sparingly soluble ionic substance with a KSP value of 6.0 times 10 to the minus 17. Recall that the KSP value, like any other equilibrium constant, describes the extent to which that equilibrium occurs. And one way we can affect the solubility of a substance, one way we could decrease the solubility of a substance, is to add a soluble source of either the silver ions or the cyanide ions. So for example, in this case, we could add either sodium cyanide to our water, and that will decrease the solubility of silver cyanide relative to pure water, or we could add silver nitrate as a source of silver ions rather, to also decrease the solubility of silver cyanide. And we can look at that with a kind of a neat simulation. So this is a simulation showing the effect of common ions on the solubility of various salts. And so if we have a flask here with presumably about 1 liter of water in it, we could choose various salts to add to it. But if we add even up to 1 gram of the lead chloride, then because the solubility of lead chloride in pure water is 4.5 grams per liter, its mass solubility, which stems from its molar solubility, about 1.6 times 10 minus 2 molar, then because we've only added 1 gram, because that's less than the mass solubility of the substance per liter, then the entirety of that 1 gram fully dissolves. So we have absolutely no precipitate forming. But if we add another substance containing one of those common ions, in this case we add potassium chloride solution. Potassium chloride contains chlorides, which is common with the lead 2 chloride salt. We can increase the concentration of a common ion, and as we do, we'll notice that the solubility is going to decrease. And as soon as it decreases below 1 gram per liter, then we start seeing precipitate form. And as we continue to add more and more of this soluble salt, it continues to decrease the solubility, which then results in an increase in the amount of solid insoluble lead 2 chloride forming on the bottom of our container. So we can also look at this quantitatively. So if we wanted to calculate the molar solubility of silver cyanide in pure water, and then compare that, kind of as a review, compare that then to what we expect the molar solubility of silver cyanide to be in 0.1 molar silver nitrate. So the molar solubility of silver cyanide in pure water is KSP value of 6 times 10 to the minus 17. This is our solubility equilibrium equation. And the KSP, as we talked about, describes to what extent this reaction occurs. So we can calculate the solubility, recall, using its equilibrium. So set up our IC tables. It's a solid, so we don't care about it. Initially in pure water, the concentration of both silver and cyanide are 0. And then as this dissociates, as it dissolves, it's going to produce 1 mole of silver and 1 mole of cyanide. So at equilibrium, we'll have X concentration of silver and X concentration of cyanide. To calculate the molar solubility of silver cyanide, then, we relate these values of X to the KSP expression. The KSP expression says that at equilibrium, when you have a saturated solution of silver cyanide, when you reach the maximum amount of silver ions, cyanide ions dissolved per liter or per volume of solution, then the product of the concentrations must equal KSP. So in this case, then, the product of concentrations is going to be X times X. And that must equal KSP. KSP is equal to 6.0 times 10 to the minus 17. So then X squared is equal to 6.0 times 10 minus 17. So finally, X is equal to the square root of 6.0 times 10 minus 17. So the square root of 6.0 times 10 to the minus 17 is 7.7 times 10 to the minus 9. So 7.7 times 10 minus 9 formally is both the concentration of silver ions and concentration of cyanide ions in our saturated solution. But because everything's a 1-to-1 ratio, this number also is the molar solubility of silver cyanide in pure water. So only about 7.7 nanomoles per liter of silver cyanide can dissolve per liter of solution for the substance. So that's the molar solubility in pure water. If we then compare that to the solubility of the same substance, but in 0.1 molar silver nitrate. So initially we set it up very similar to the week before. We set up IC table. Okay, for the solid, and this is pure. This is no longer pure water. This is now 0.1 molar silver nitrate. So initially, yes, we still have 0 concentration of cyanide initially, but we have 0.1 molar concentration of silver ions. So that's the difference between the calculated solubility of the substance in pure water, 0, 0, versus calculated concentration of the substance in the presence of a common ion. Exactly one of these will be non-zero. Otherwise, we approach the same way. So as this dissolves, it will increase concentration of silver ions by X, also increase concentration of cyanide ions also by X. And then so at equilibrium, we have 0.1 plus X. Cyanide concentration is 0 plus X. And then from there, it's the same thing. So KSP, the saturated solution, is equal to the concentration of the silver ions times concentration of cyanide ions. So then KSP value, our 6.0 times 10 minus 17, is equal to the concentration of silver, which is 0.1 plus X, times concentration of cyanide, which is X. So at this point, we want to solve for X. And we can do so by distributing X through 0.1 plus X, and then we get a quadratic equation. And then, well, not a quadratic equation, we get a X. Well, actually, you do get a quadratic equation, and then we can solve for X from that. Or, because we noticed that in the previous problem, the X was very, very small, as we'd expect, because KSP is fairly small. And we know conceptually that when you add a common ion, that's going to push the equilibrium a little bit to the left, decrease the solubility. So we know that our value of X in the second problem is going to be anything but it's going to be everything but less of this number. Otherwise, a very, very small number. So we can make the simplifying assumption. We can assume that whatever X is, it's going to be much smaller than 0.1. And we've seen this before with weak acids, weak base equilibrium. So if that is true, then 0.1 plus X is approximately equal to just simply 0.1. So that simplifies our calculations a little bit. So now the equation becomes 6.0 times 10 to the minus 17 is approximately equal to just 0.1 times concentration of cyanide, which is X, or 0.1X. So then X is going to be equal to, divide both sides by 0.1. And so we get 6.0 times 10 to the minus 17 divided by 0.1 gives us 6 times 10 to the minus 16. 6.0 times 10 to the minus 16 molar silver, or molar silver cyanide solubility. That is a concentration of cyanide. Concentration of silver would be 0.1 plus this number, which you can see is very similar to, which is basically the same as just 0.1. So this would also be the molar solubility of silver cyanide, but in a 0.1 molar silver nitrate solution. So the concentration did go down as we'd expect. Even without checking, we know this number is very, very small relative to this number. And it went down, in this case, about 7 orders of magnitude. So it's about times 10 to the minus 9 molar solubility in pure water. It's 10 to the minus 16 molar solubility in a 0.1 molar silver nitrate solution. Another factor that can affect the solubility of a substance is the pH of the solution. So with pH of solution, we talked about, I believe it was last chapter, about acidic salts or basic salts or neutral salts. Ionic compounds with acidic cations are going to be expected to be more soluble in basic solutions, whereas ionic compounds with basic anions are more soluble in acidic solutions. And we can see why that is the case. If we take a look at something like calcium fluoride. Calcium fluoride would have a particular solubility. Calcium ions and fluoride ions. And the extent to which this reaction occurs is given by the KSP of calcium fluoride. So if this were in pure water or neutral solution, then this is the only relevant equilibria we need to worry about. But if this is done in a acidic solution, then in an acidic solution, you also have a high concentration of hydronium ions. So another relevant equilibria is that even though the calcium ions are neutral, fluoride ions are basic. So the fluoride ions, being basic anions, will react with water to a certain extent to produce HF and hydroxide ions. And this is given by the Kb of the extent to which this reaction occurs, it's given by the Kb of the fluoride ion. So in a acidic solution, what do we know? Acidic solution, that means it has a high concentration of hydronium, otherwise it wouldn't be acidic. And because it has a high concentration of hydronium, know the concentration of hydronium and concentration of hydroxide are always inversely related to one another. So that means that the concentration of hydroxide is going to be low. And the concentration of hydroxide is low, and that's going to pull this Kb equilibrium to the right. Because this concentration is low, that's the principle. The concentration of product is low, that's going to pull the equilibrium to the right, try to make up for that lost concentration. If that pulls this equilibrium to the right, that's going to effectively decrease the concentration of the fluoride ion. And this fluoride ion is exactly the same as this fluoride ion. So by this equilibria, that keeps the concentration of the fluoride ions low. And so this equilibrium shifts to the right to a greater extent than it otherwise would in order to make up for that lost product. So in other words, as we net resolve all that, is that the solubility of calcium fluoride will increase in the presence of an acidic solution or the presence of an acid. And we could prove the same thing of ionic substances with basic anions. I'm sorry, with acidic cations rather, are going to be more soluble in basic solutions. So in short review, we have our common ion effect. Common ion is always going to decrease the solubility of ionic substance in the presence of a soluble source of either the anion or the cation. We proved that, looked at qualitatively as well as quantitatively. And with a pH solution, that's only going to affect solutions which have either an acidic cation or a basic anion, and we can predict the effect of the solubility there, where we either increase or decrease solubility based upon how the pH of the solution compares to the nature of the ionic compound, whether it's acidic or basic.